And good afternoon, everybody. I'm Jim Shafer. I'm with both Laminar Flow and Power Flow. A lot of you folks I have met before or seen before at the Cherokees to Oshkosh. I'm one of those nuts that loves Oshkosh. I've been going for 18 years. All I ever do is work my butt off, but I can't wait for the next year to come around and do it again. And that's where I met Jan, and I want to thank him for inviting me here for your group. It's sort of funny because PowerFlow obviously does the tuned exhaust systems for many aircraft. We don't happen to have them for the PA-32s yet. We will eventually, I can't tell you when. So when Jan called up and said, hey, would you like to also support and participate in the PA-32 fly-in? I said, well, sure, I'd love it. That's the kind of stuff I live to do. But my first thought was I don't have anything for that airplane. And then I got to thinking, PowerFlow doesn't, but Laminar Flow does. And it's sort of a weird story there. I'll go very briefly. But Laminar Flow was actually the first company started by Robin Thomas back in 1983. And it's been sort of his pet project, almost like a hobby, more than a business ever since. But they do make really good products, and they have a very good installed base. So after I got to thinking, I told Jan, well, I can't talk about the tuned exhaust too much for your airplanes, but I can definitely, give you some background on the Laminar Flow product. So that's why I'm here. And the talk is on bang for the buck, because the beauty of aerodynamic improvements is they will give you roughly the same horsepower gain as a tuned exhaust will, which is in the range of 15 to 20% efficiency, but they are a fraction of the cost of any other option out there. So I'll get started on those. And I'm Jim Shafer, as I just said, and been with PowerFlow since 2008, and I love it. And the one thing I really love about it is I've never had to hide from a customer. Everybody I've ever talked to or has put either a PowerFlow or a Laminar Flow product on their airplanes, they absolutely love it, and they are our best salespeople. So, personal background, I'm a private pilot. I've been flying gliders since I was 14. Been flying tunnel jumpers since I was 16. Just never stopped. It's my drug of choice, and that's what I like to do. A little bit about Laminar Flow systems. Robin Thomas, you see him both on the left there and on the right. He started Laminar Flow. He looks like a beach rat, and that's basically what he was. He washed up on the shore of the British Virgin Islands after traveling the world, and he had a Piper Seneca that he bought and was running a charter operation, flying tourists all through the Virgin Islands. And he very shortly found out that the book numbers he was using for pre-flight planning on those flights over water bore absolutely no resemblance to the actual performance he was getting out of the airplane. And he was sort of scratching his head for a while. He was a mechanic, not an engineer, but a real good tinkerer, and he started looking at what might be wrong with that airplane that he couldn't get the book numbers out of it, and he found 5 or 6 major things that he thought he could fix. So he started tinkering around. He was not ANPIA, and he was 1,000 miles away from the closest FSDO, so he started bolting stuff onto the airplane and see what worked and see what didn't. If it worked, he left it on and started telling his friends about it. If it didn't work, he wouldn't waste any more time on it. And we'll go into more detail on that later, but the beauty of it is he very shortly started making a whole lot more money selling these speed mods to other Piper owners than he could ever make flying tourists around the Virgin Islands. So he moved the whole operation to Daytona Beach in Florida, and has been there ever since. And that's where PowerFlow also got started about a decade later, after he had made a good business out of Laminar Flow. So Laminar Flow is the oldest manufacturer of STC speed mods for the Pipers. All the other folks that got in later, Low Presti, Knots to You, 2 or 3 others, they all took a look at what Robin was doing and thought, well, we could probably do that cheaper. So they did. They didn't do it better, but they did it cheaper. And I'll go into that too. So the beauty of it is the way Robin worked is he would not put anything on an airplane that he had not personally flight tested and he had not personally measured a gain of at least 1 mile per hour. Any speed mod, it's an incremental gain. Everything you get is a little bit more than you had before. So very few silver bullets out there as far as improving aerodynamic efficiency, which is what we're trying to do. But if you do them one at a time, and test them all, you do end up with a pretty healthy gain on the PA32s and the PA28s. The total max gain is in the range of 15 to 20 miles per hour if you put all these on. And as I said, we've been selling them since 1983, and there's over 1,100 of those kits installed and flying. Another good point is when you put on a speed mod, it basically becomes part of the airplane. Zero maintenance costs as far as keeping it on the airplane, and we've had customers flying their laminar flow equipped aircraft for several decades now. All right, so what is laminar flow and why do we put it in the name? Basically, most pilots know instinctively a streamlined shape is going to fly better than a bulky, clunky shape. And the diagrams here just show you a flat plate is very draggy. A cylinder gets 50% of the drag of a flat plate, and a streamlined shape is 10% of the form drag of a flat plate. And what we're looking for, what we're trying to remove anytime we do a laminar flow improvement, is that drag bubble downstream of the object, whatever it is. So if you can reduce that from 100% to 50% to basically 10%, you do get some pretty impressive performance benefits. And obviously the most iconic example of that is the P-51 Mustang. And this is actually a picture I shot at Oshkosh, and I'll second Ed's opinion. Oshkosh is Disneyland for any pilot, and for me, it's like paying a kid to go to Disneyland, because I go there every year and get paid to do it, so that's great for me. But in any event, I was wandering through the Warbirds a couple years back, and I noticed this P-51 is beautifully polished, and then I saw the heat trail from the exhaust system. And I've heard numerous, I'm always a P-51 fan, I guess most pilots are, that's probably your dream airplane. And a lot of guys were saying, well, they said it was laminar flow, but it really wasn't. I beg to differ. This photograph, as far as I'm concerned, shows that it really was laminar flow, because you can see where the heat from the exhaust tempered the aluminum and discolored it. But look at the flow there. There's absolutely no turbulence from the lead. The exhaust flow followed the wing form exactly from the lift, and there's absolutely no turbulence bubble over the length of that wing. So that's why it got the range and the performance that it did. And those are the performance benefits in a nutshell that a laminar flow design can offer you on any airplane. And why does it matter? Okay, so we all fly airplanes, we all want to get the most performance out of them as we can, but as pilots and owners, there's very, very, very few things that we can do. The lift is sort of baked in by the aircraft engineer when he designs the airplane, or the team. So you've got a given wing cross-section and airfoil, gross weight, Reynolds numbers, all that information you're not going to touch when you go to fly the airplane or modify it in any way. Same with gravity. If you figure out a way to change that, let me know. I'm right there with you. But you're sort of stuck with that force. Leaves two, thrust and drag. And thrust is theoretically possible to change as an airplane owner, and depending on what kind of airplane you fly, you may have the option of adding a bigger engine, putting in inducted fuel injection instead of carbureted, or supercharging. But the FAA might have something to say about that, and your wife might have something to say about that too, because most of those options can get pretty pricey, and not all of them are available for every airplane. If you're flying a certified aircraft, whatever you want to do, it's got to have at least a field approval, preferably an STC. It's got to be certified and approved by the FAA. The other thing is, even if it is available, the odds are it is going to get pretty pricey, and I'll go over that in a minute. So the advantages with increasing thrust there's a few of them. Number one is it is well proven. You're not breaking any ground. No, there's no replacement for displacement. That's an old aviation adage, and it's basically true. If you want to get more performance, bolt on a bigger engine. It will give you more performance, no question. There are a whole bunch of reliable sources out there for bigger engines, improved efficiency, one or the other. And I have personally, in my 16 years with PowerFlow, dealt with most of them and a lot of their customers. And I can tell you, most of these guys are pretty sharp, and they are legit, and their upgrades will work. I've talked to Lycon, Airplanes, Penyan, and quite a few others. I haven't run into anybody that I would hesitate to refer people to If they're looking to do an engine upgrade, there's a lot of guys out there that will do a good job for you. It's not going to be the most inexpensive upgrade you ever do, but it will probably do what they tell you it's going to do. The beauty of that is, what I say is it does improve the utility of the airplane if you're looking to increase useful load or speed or altitude or whatever. It's not going to improve the efficiency at all, but you will get the utility gain that you're looking to get. The disadvantages are the high initial cost. And I really just started looking at this a couple weeks ago when I found out I'd be giving this talk. So you folks may have better numbers, and if you do, feel free to shout them out. This is what I got out of a cursory exam, search of the internet about 2 weeks ago. If you want to add a supercharger, it's about $25,000 plus the install for a supercharger. That'll usually pick you up about 15 horsepower. If you want to go from an O540 to an IO540, which picks you up about, I believe, 40 horsepower, that's about $70,000 for that upgrade, plus the install time. And the install time on that's probably 2 or 3 weeks. And if you want to go to an TIO, a turbocharged IO540, that's 175 grand, and the upgrade's probably another 3 or 4 weeks on top of that. Now, any of those options are also going to increase your maintenance and repair costs, because whereas you can take your typical IO540 or O540 basically anywhere to get it rebuilt or maintained or repaired, most of these upgrades, you're looking at more specialized equipment, better training, higher level of maintenance and repair costs. Since a lot of them also involve higher temperatures and pressures for the engine, your TBO typically comes down, and there's a performance trade-offs for the performance you get. Typically, you're looking at a higher fuel burn, which results in decreased range for the airplane. The increased empty weight of the equipment or the bigger engine results in a lower useful load for the airplane. So if it does what you want it to do and you're comfortable with the trade-off, that's fine, but you just want to be aware of what it is that you're trading for. And again, depending on the airframe, and again, I'm sure you folks know more about this than I do, what's legal and approved for the PA-32. Some of those options aren't. I don't think you can get a supercharger. You can't go from an O to an IO, and I don't know if there's a STC to put a turbocharged engine on an aircraft that didn't have that to begin with. There may be, I honestly don't know. So just to give you an idea of how this works in practice, I got the book specs from the PA-32-300, and there's certain crucial numbers that I'll be referring to later in the talk, and these are the baked-in factors that I mentioned when talking about the design of the aircraft. That's the wing area, the airfoil, the empty and the gross weight, and the power plant. Those are all what you had to start with, and they result in these performance numbers. A max speed of 174, cruise speed of 168, service ceiling of 16.2, and a rate of climb of 1,000 feet, about 1,050. For the PA-32-300 drivers out there, does that basically jive with what you see, or is that wishful thinking? Okay. So that's what I based the analysis on, and if I knew what all these numbers meant, I wouldn't be up here. I'd be out designing airplanes for NASA or something. But these are numbers generated by a friend of mine who does have a master's degree in aeronautical engineering. And I told him what I was trying to do is calculate how much of a performance gain you would get for different horsepower increases in the engine. And he ran the whole numbers with the coefficient of drag and the coefficient of lift and the additional horsepower. And I've got copies of these here if anybody wants to take a look, but I just wanted to give you a basic idea. I asked him if you wanted to get another 15 miles an hour out of that PA-32-300 airplane, how much more horsepower would you need to generate to get that gain? And he ran the numbers for me, and essentially he found out if you wanted to get another 15 knots out of a PA-32, you'd have to get a 366 horsepower engine and install it on the airframe, and that would give you that gain. If you wanted to go up, increase in the rate of climb by 200 foot per minute, you'd only need another 26 horsepower out of the engine. So it'd be 326, 327 horsepower to get you a 200 foot per minute rate of climb increase. And then he laid it all out in a table for me, and I'll compare that to what with the other numbers shortly, but basically at the 300 horsepower level, it's 168 miles per hour, which is the book value, and then that increases, not logarithmically, but pretty drastically. If you want to go 178, which is just a 10-mile-an-hour gain, you're looking at 50 horsepower to do that. So that's the basic. So that's the basic gain possible by increasing horsepower. So that leaves the other option that I wanted to look at, which is improved aerodynamic efficiency, which is the most easily accomplished by reducing the drag, and we'll go through that now. So the advantages to that are also, it's pretty well proven. I used to do this as a kid, and you may have to stick your hand out the window of a car, lay it flat, it goes pretty good. Open it up, try it, opposite the wind flow, and it just gets pushed right back. So that's the way it works. It's not real hard to figure out. There are a lot of good options for reducing the drag on an airframe, and a lot of them are STC for the PA32 and in all the variants. Once it goes on the airplane, it's done. No maintenance additional required. It stays on the airplane. We've had customers, as I mentioned, that have had these on their airplanes for 20 to 30 years, and they don't even know it's there anymore. There's no weight penalties for reducing the drag, or reduction in useful load. Whatever numbers you have now, you still have those numbers when you're done. And there's no increase in engine temperatures or pressure, so you're not inducing any other stresses to the airframe or the engine. You're really just letting both of them work a little bit better, more efficiently. So the one good advantage of improving the aerodynamic efficiency is you get the performance gain throughout the flight regime, from takeoff, climb, cruise, service ceiling. It's all there. You get, if it's a 15% efficiency gain, it's across the whole great realm of flight. And when we added it up with all the mods available, you can do them all at once, or you can do them one at a time, whatever suits your purposes best. But it adds up to a 14 to 17 mile per hour gain in cruise speed and up to 140 feet per minute in the rate of climb. That also reduces the fuel burn, and again, it's efficiency. You can take it however you want. You can go faster, or if you're happy with your current speed, it takes less throttle to do it, and it reduces the fuel burn and increases your range. Another nice little benefit is, since the airframe is cleaner, the control surfaces work better, the control authority, particularly at high angles of attack and low airspeed, is much better. And again, the lower initial cost. It's less than or equal to 10% of the cost of increasing the horsepower for the same performance gain. And just round numbers, for a PA32 kit, if you put everything we have for that airplane on it, you're looking at $2,600 plus installation time. And if for a retractable, it's $4,500 again, plus the install. And depending on what you do, I'll go over to that later, what the install times for most of these are. Most of the kits, it's 2 to 3 hours per kit. The one more labor intensive is the wing smoothing kit, and that can go as high as 40 hours. But again, it's a one-time deal that we've done. And we also have a pay-as-you-go option. Essentially, we offer a discount for buying the entire kit, but you don't need to. If you're a little bit skeptical, you want to say, hey, does this stuff really work? There's a couple you can buy to try it out and see how it works on your airplane, and then once you're comfortable, once you see the gain, then you can add the others as you go. I have a lot of customers who will just, as a rule, they'll buy one kit a year, put it on, and then they'll do it slowly that way. The disadvantages of this approach. The main one I would say is that user discretion is advised. There's a ton of people out there selling speed mods. Not all of them are the same. The delineating factor in my mind is, have they been flight tested? If they have been put on an airplane and before and after numbers have been generated, and those numbers say, yes, you will see the gain, then the odds are you will see it too on your airplane. As far as I know, Laminar Flow is the only company currently making speed mods that has actually put each and every one of them on an airplane. And I would say, honestly, they don't all make the cut. We've made a lot of speed mods and tried them out. You know what? We didn't see any gain. It looked neat, good fashion statement, but it didn't give you any performance improvement that we could measure. So they're not on our product list if they haven't been tested. And I used to work for Lopresti before I started with laminar flow, and Jim Lopresti was the engineer when I was there. He called those fashion statements. They look slick, they do absolutely nothing for you. There's also the law of diminishing returns, which you have to be aware of. A lot of speed mod companies will list this and this and this and this with a performance gain for each one, and you add up all those numbers, and pretty soon you're doing more factor 9, you know? And you know that's not possible, and it isn't, because what happens is the max gain that you can get depends on the airframe and how dirty it is currently. And every time you add a speed mod, you have less remaining gain available to get. So every time you put on another one, you're going to get less and less and less until eventually you've got all there is to get. You're not going to get any performance gain. And no matter what you do, again, the bottom line is we're flying PA-32s, we're not flying P-51s. And nothing you're going to do is going to change a PA-32 into a P-51. So you sort of got to be realistic on your expectations. And that's what we try to do with our performance numbers as well. The other thing is installation can be labor intensive. Most of it's not real, you know, complicated or sophisticated. Most of it's sheet metal work and riveting on pieces and so forth. But a lot of our pilots do it themselves under the supervision of an IA, because these are STC'd items. When you're done, it is going to have to be signed off in the logbook. But if you're not familiar with it or you don't know what you're getting into, it can be a bit of a shock, and it might be easier just to hire it done, depending on your degree of comfort in doing this kind of work. And the one thing I do want to point out is the one labor-intensive kit is the tank fairing and wing smoothing. That is the single biggest improvement gain you can get from any of these, but it is also the most labor-intensive. And when you do the wing smoothing, I'll get into that more detail. You really look at repainting the wings after we're done, but I'll go into the details on that shortly. Okay, so the theory behind all this is a properly designed speed mod improves the L/D, and that's a measure of an airframe efficiency, and therefore the performance by reducing the drag coefficient, the lift-over drag ratio, and delaying the transition from laminar flow to turbulent airflow over the wing, and then by ferrying any protrusions that are basically drag pockets on the airframe. And when I say properly designed, there's really one good concrete example that I like to use. This is a laminar flow flap hinge fairing. And if you just in your mind, this is the leading edge of the wing here, this is the trailing edge here. If you visualize the air flowing around that protrusion, you can see the whole thing is faired in very nicely, and just like that flat plate illustration at the beginning, the air is going to stay attached at the beginning, over the transition, and at the end. So when you're downstream, you don't have any of those drag producing burbles that you would normally see. This will go unnamed, but this is one of the competitors' flap hinge fairing. And I grant you, it looks cool. It's nice and streamlined, looks neat. But again, if you visualize that same airflow, it's coming over here, it stays nice and attached on this portion, and then it drops off a cliff because there's no aft hinge fairing portion that will allow that laminar flow to maintain and stay attached to the airframe. So you've got a great big drag bucket right there, and that's what they think is going to improve performance. One thing that this tells me is they never put that on an airplane in test fluid, because if you did, you would see right off that airplane is better off without that fairing. If you put that on your airplane, you're actually creating drag. So that's why flight testing is crucial wherever you get. You want to make sure somebody put it on an airplane, somebody had the numbers tested, and somebody will show you those numbers. So how does it work? Why does laminar flow, why does increasing the aerodynamic efficiency work so well? And what I do, I'm not an engineer, but as I said, I am a sailplane pilot. And what we do, and what I have found is actually one of the best overall measures of aerodynamic efficiency is the L/D, or the glide ratio of any given airframe. That will tell you how efficiently that airplane moves through the air and what is the cost in energy when it does so. Lift is coefficient lift measured in units of horizontal distance, and drag is the coefficient of drag measured in units of vertical distance per foot traveled forward. So I like it. It's a practical rule of thumb. You don't have to calculate a whole bunch of variables. Just look at the L over D, and that'll tell you how efficient that airplane is. And these are the ones that I personally have some experience with, and you folks also. I'm partners in a J3 Cub, and the best glide speed on that airplane is 50 miles an hour, and at 50 miles an hour, it's coming down at 500 feet per minute. And that calculates out to a max L over D, a glide ratio of 7.5 foot forward for every foot of altitude that it loses. One you folks have most experience with, not quite. We talked about a bowling ball earlier, and that was well said, because the 32-300, the best glide speed is 100 miles an hour. At that speed, you're coming down at 1,250 feet per minute. Like I don't know what a bowling ball is, but it's probably close. And that gives you a max L over D of 7.0 to 1 on that airplane. So 7 feet forward for each foot of altitude you lose. My personal drug of choice is this beast right here. It's a sailplane that I've owned probably for 20 years or more. Home built, wood and fabric, designed in the 1950s. So this is by no means state-of-the-art sailplane wise, but it sort of makes the point. Best glide speed on that is 50 miles an hour. At that rate, it's coming down at 165 feet per minute, and that calculates out to 27 feet forward for each foot of altitude you lose. So that's a fairly efficient airplane. There's now gliders out there that'll go 50 to 60 L over D, 50 to 60 feet forward for each foot that it loses. So if you want to compare, that's a good way to do it. And what I did here is I looked at improving the efficiency of the airplane as opposed to the increase in the horsepower that we did earlier. So again, if we look at the 168 miles an hour as the baseline for 300 horsepower, and over here the 168 miles an hour is what you're getting at with that airplane the way it is. So let's say you wanted to go 10 miles an hour faster. So we go down to 178, and you would have to reduce the drag on that airplane by 16% to get 178 mile an hour gain. If you wanted a 10 mile an hour increase with increased horsepower, as I said earlier, you're gonna go, let's see, 300 and 350. Again, you have to add 50 horsepower to get the same gain you can get by just reducing the drag by 16%. So that's why these things are so cost effective. And for the PA32 series, we have a bunch. The flap gap seals, I like this one. I call it double bang for the buck. Reason being, and particularly if you're one of the skeptics, and I typically am too when it comes to performance gains, if you want to see how these things work, this is a really good place to start. Because I think it's about $400 or $500 for the Cherokee 6. You put it on, and you get two benefits right away. The way the wing works, obviously, everybody knows there's higher pressure on the lower edge, and reduced pressure on the upper surface of the wing. But that high pressure migrates through the seal, through the gaps in the control surfaces on the flaps and the ailerons. And when that high pressure hits the curved portion of the airfoil, it creates drag. The other thing it does is, particularly at high angles of attack, that drag burble interferes with the control authority of the elevator. So the flap gap seal solves both those problems. It eliminates that high pressure air migrating from the lower surface to the upper surface, and when the nose is up and the wing is generating most lift and blanketing the airfoil over the elevator, it eliminates that. So you do have greater control authority at high angles of attack, low airspeed, and it reduces the stall speed. So if you want to see, this is a great proof of concept. If you're not sure of the speed the mods work, put one of these on and you'll see exactly what we're talking about. The other options we have, or one of the others, is the aileron gap seal. Basically does the same thing. It'll gain you 1 to 3 miles an hour in the speed and the 25 to 50 per minute rate of climb. And again, any wing designed, and I'll go back to that sailplane real quick. Okay, if you look at that silhouette, there's no daylight. This is actually a laminar flow wing too on that aircraft. But there is no way for high pressure to migrate from the lower edge to the upper edge. And as a benchmark, actually, I looked it up. There's a version of this same sailplane without a laminar flow wing, but instead of the 27 to 1, its book value is 22 to 1 with with the max L over D. So the laminar flow wing does make a difference.
So this last one you're showing, that's on the horizontal stabulator? Or are you still talking about the wing?
This is the wing. This is the wing still. Sorry. So yeah, but this is the other option you have in addition to the flap cap seals. You can put aileron cap seals on, and it does the same thing. You're trying to prevent the migration from the high pressure air from the lower surface up to the top surface. Flap hinge fairings, again, very simple. There's 6 pair on the PA32. Basically, they're all riveted on. It's a gain of 2 to 3 miles an hour. Pretty easy installation. It's the same aircraft grade aluminum that your wing is made out of. So once they're on there for life. You never have to take them off. The other one that, as I mentioned earlier, does give the biggest performance gain, but it is also the most labor intensive. And this is Rob and Thomas installing it on a Cherokee that I believe AOPA flight tested, and they got some pretty good improvements in performance on the PA-28. But basically, with what Robin noticed when he was flying in the Virgin Islands, first thing is that the Piper wing is designed to be laminar flow, but the way Piper built it in the factory, it does not achieve laminar flow. There's just too many imperfections in the airfoil. So the first thing he did when he was trying to improve the performance of his Seneca in the Virgin Islands is he said, well, let's see what happens if I actually make that wing laminar flow. And he did 2 things to it. The first one is he put these tank fairings on there. And this is so counterintuitive. I thought the same thing. How could that possibly make a difference? Well, it turns out that it does, because on the Piper wing, the front 30% is where the laminar flow happens. After that, the airflow actually does detach after that, and it is turbulent. But on the wing, the way it is, it's turbulent the whole way over. There's no laminar flow whatsoever. So what happens when airflow encounters any kind of imperfections in the airfoil, it transitions to turbulence. So he wanted to eliminate that, and the first obvious target was the row of rivets and screws around the fuel tanks. So he developed these fuel tank fairings to cover that up and restore the laminar flow in that portion. And that worked pretty well. So he said, okay, I got that done. He picked up about 4 miles an hour in the flight test before and after just with those fuel tank fairings. And he says, now let's see what happens if I make the whole wing laminar flow as much as it can be. Again, it's only going to be about 30%. Yes, sir?
Yeah, it's hard to see in the pictures from here, but you're talking about that little triangular rubber piece that's on the front edge of the wing?
No, sir. And I've got a sample of one here. I'll be happy to show you after the talk. It's actually right here. They're both white. Some marketing genius painted them both white. But it is these straps that cover the row of rivets and Phillips head screws that cover the whole the tanks in. Good question. And I didn't know this yesterday, but I found out. Basically, every 4th screw that's in there right now, we use to anchor the tank fairing in there, and we countersink the hole. So we just do a longer screw and pick up the same hole that's in the tank and hold the tank in already. So it's a lot less of the drag and it's countersunk. So essentially it's still laminar flow. But the beauty of it is that means if you do need to remove the tanks, these things pop right off. You don't have to worry about grinding them off or anything like that. Okay, so to get the laminar flow over the rest of the wing, that's the hard part. That's the labor-intensive part, and that's the part I mentioned. You probably want to plan on repainting the wing when you're done. Because what he came up with was this very simple caliber gauge which measures the imperfection of the wing. And I can't remember what the variation is allowed, but he figured it out. To maintain laminar flow, it's got to be like 0.02 inches across the surface, and that's what that gauge tells you. And then what he did is he got a mixture of Bondo, auto body Bondo, and micro balloons. And he just coated the whole wing with that, and he just shapes it, gradually sands it, shapes it, gradually sands it, until he gets, number one, a nice mirror finish, as you can see, but the tolerances, the variations, it covers up the butt joints or the lap joints, which are terrible, and all the rivet heads and screws and all that are on that wing. He fills them all in. And that's what takes the time, and it can take 40 to 50 hours from somebody who sort of knows what they're doing. We have found out from experience that auto body guys are great at this. They can do it in their sleep. And then you've got the laminar flow where you need it. He paints the wing, and with that, you pick up 15 miles an hour on that wing between the tank fairings and the wing smoothing kit. Yes, sir.
So he's changing the shape of the leading edge of the wing a little bit and smoothing it, and it's only the front third of the wing he's doing this to, or?
It's the front third, and if you look at the wing, you'll see where it's smooth sheet metal, but the metal overlaps, and there are the screws, any of them. Go look at any Piper, Cherokee, PA-32 wing. You'll see the same thing.
Oh, no, I meant one of these that's been done.
Oh, I'm sorry, no, I don't have one here. I can give you the reason why, but in any event, no, we don't have one here, but if you look at a Cherokee 6 wing, you'll see why it works and why it's needed. To answer your question, he doesn't actually change the airfoil, he is restoring it to the tolerances that it needs to be in order for laminar flow to be possible. So it's the same airfoil, it's just smoothed out and then painted essentially.
So
Any
is
other
this
questions? Yes, sir.
Is this for all the wing forms of the PA-32?
Yep,
The Hershey bar and the cable?
correct.
Yeah.
Yep. Okay, and the other thing we have for the retractables is the wheel well fairings, and again, same thing. In this case, the leading edge will be here. The wheel retracts, but it stays on the bottom of the wing exposed. And basically what you're doing is you do have laminar flow over the leading edge of that tire as it's there, but then you have the drop off where normally if you don't have a wheel well fairing, you got the drop off on the downwind side, and again that's where the drag producing burble would originate right there. And the fairing just fairs it, streamlines it in, so the airflow stays attached after the wheel until it exits the wing. So again, this is a pretty easy one to install, 3 to 4 hours to put the kit on, and you gain 3 to 4 miles per hour. And the same thing with the others, it is aluminum, aircraft grade aluminum, and they never need to be removed for maintenance. And of course, proof of any speed mod is what do the people who have it think, and I'll leave that up there if you want to come up and look. But basically, we've had guys who have had these on there for decades. One of our first customers, Tom Hagan with the Piper Lance, he bought the whole kit, but he used his airplane commercially, so he only had time to put on the tank fairings that I showed you earlier, and then he had to go fly, and he said he saw 7 knots at 70% cruise just from those tank fairings alone. And then as time went on, it took him about a year to get the whole kit on. But after 500 hours of flying with a year, you saw a 15-knot increase with all the kits installed. So I think that's about it, unless anybody has any other questions. Yes, sir.
The fuel tank strips for the screw, does that give height to that in respect to the rest of the wing?
Yeah, it is a little bit higher in
How
profile.
does that affect the airflow?
I'm
How
sorry,
does that affect the airflow, having a ridge that?
Not at all, because again, what he did is he followed the formula for laminar flow and stuck with it. You can have transitions and you can have variations, but the transition has to follow certain parameters. You don't want a steep gain and a steep drop off in altitude. It's got to be fair in.
One more question. I know some of the engineers that design space station with their kids would race the Sabbath.
And I'm sorry, I cannot hear.
Okay, some of the engineers I worked with when we designed the space station, their kids raced Sabbaths, like at Newport Beach. Those were those little squarish sailboats.
Oh, cool.
And they would take wax and rub it on the bottom until the bottom's really rough. Because they didn't want it. They wanted a turbulent flow underneath because that reduced drag. So can you speak to that at all?
That's a great question. And as a sailplane pilot, we do the same thing. We call them turbulator strips. Sometimes these these surfaces can get too slick to the point where the air cannot adhere to them anymore. You don't have a boundary layer, essentially. So a trick that people way smarter than I came up with, it's a little piece of one-sided sticky tape with very minute imperfections essentially. And it creates just enough drag so that the boundary layer stays attached. Because what some guys with those really high performance sailplanes, they fly them in contests, they would lose control of authority because the air couldn't stick to the aileron. It was so damn slippery, the airflow. So they put little turbulator strips just upwind of the aileron. And essentially they do the same job as the microvortex generators, which also work, by the way. It's a very well-known, very good fix. And there you create just enough turbulence so the airflow stays attached and the control surface works, but you don't slow down the airplane.
Yeah, they do the same thing with surfboards. They make the bottom rough with
Yeah, exactly. Any other questions?
Wheel head fairings? What kind of
Yeah,
performance?
yeah, thank you. Laminar flow does have some very good fiberglass fairings, strip fairings, that kind of stuff. We are unable to produce them right now because the guy we had making them was doing them for 50 years and he retired. So we're looking to qualify, and we've been trying to qualify. We don't put out crap, so if we can't get the quality where we need it, we won't ship it. And that's where we are right now. But the president of Laminar Flow and Power Flow is actively searching to find somebody who can do the kind of quality we need. As soon as we do that, we will reintroduce those.
So what were you seeing in terms of performance or performance improvements versus, say, platter, aileron and platter?
Okay, so for the Piper, yeah, there's two versions of that kit, and I can give you the detail. I don't even have the details with me. So one version is called fancy pants, and then what we do with those is reuse your current speed pants over the gear and add another piece that bolts to that essentially, and fares in the brake calipers and the lines and all the crap that's hanging out in the breeze. And those pick you up about 3 to 4 knots for the set for 2 wheels. We did the same thing for the nose gear, have a nose fairing that covers up the shock absorber and all that. Robin also actually developed a pressure recovery speed pan. Yeah, and those aren't available either, but when they are, they pick up like 5 to 6 knots over the standard Piper wheel pan, and they're about 10 knots over a bear strut. That's easy to beat, but yeah, it was a significant improvement over what Piper can do with their standard wheel pans. Any other questions?
I have a lot of these on my airplane if anyone wants to take a look at them.
Great.
With the exception of the tank ferret.
Okay.
What's your tail
Yeah.
number?
And I'll be back.
61, November. Green machine.
Cool. And I'll be here all day back there or floating around. So if you have any questions or you want to see any of those calculations, come on back. I'll be happy to talk to you. Thank you very much.